Good morning to everybody. So my lectures here will be of a very introductory nature. So I'll talk about first order gradient and subgradient based methods for optimization. I'm a little embarrassed to talk about these topics in front of people like Boris and Yuri and Arkady. But I didn't know that, about this before. So please excuse me if some of this concept will be totally elementary for you, but maybe for not. I didn't know about the background of all students in this class. So maybe for some of you, some of these ideas will be new or partially new. And also I take the occasion to do some advertisement because some of the topics I will present are taken from this new book on optimization models that is coming out in September. It's called Optimization Models by my friend and colleague Laurent Elgaoui and myself. Okay, so let me start from a very elementary topic. What a gradient is. Okay, so we have a function from Rn, so from vectors in n dimensions to R, which is differentiable on its domain, and we are given a point at 0. And what we call a gradient of function f at x0 is denoted by this symbol. It's just the vector of partial derivatives of the function evaluated at x0. And this is a column vector. And if we do a first order Taylor series expansion of function f at x, at x0, then we have the value of the function at x0. This is the gradient multiplied by x minus x0 plus terms that go to 0 faster than first order as x approaches x0. And a key concept is that the gradient of the function at x0 is orthogonal to the tangent plane or hyperplane of the level set of f at point x0. And a key characterization of convexity for function f is that, well, if f is differentiable, then this fundamental inequality holds for this function, which means that the values of the function f at any point y in the domain is larger than essentially this linearized version of f. So f computed at x plus the gradient times y minus x. And geometrically, the interpretation of this condition, of this convexity condition, is that the graph of the function, of a convex function, is always lower bounded by the tangent hyperplane. At any point. So any point we choose in the domain, then the graph of the function is lower bounded by this hyperplane, by the tangent hyperplane, for any convex and differentiable function. So there are a couple of important consequences that we can draw just from this elementary characterization. Maybe I can also use this. We have something happened. We have a point x, and we compute the gradient of some function f at x. Only this one point and the gradient. And immediately we can divide the whole space into half spaces that I name there H++ and H minus. And H++ is the part of space of vectors or points y such that y minus x forms a positive inner product with the gradient. And the other half space here that I call H minus is the set of points y that form a negative inner product with the gradient. So one point and the gradient, and we divide the space into half spaces. And the important fact, the fact that this is important in optimization is that actually any point that we may choose here in this half space, due to the characterization of convexity that we showed in the previous slide, is such that f of y then is greater than or equal to this quantity here, due to the previous characterization. And if this inner product here is positive, then this is strictly greater than f of x, which means that no point in here can provide a value of f smaller than f of x. And this is very important because, of course, when we will try to minimize f of x, and we are at a point here, and in some iterative algorithm we are looking for points of lower value of f of x. Well, this means that there is no point in looking for these minimizers in this half space. Sorry. Okay. Because all points in this half space will actually give us values that are no smaller than the value that we already have here. Okay. On the other hand, if we take any point in this other half space, h minus, like a point in here, if we take y here, then this any point in here defines a direction, like this line here, and I denote this direction by with a normalized vector, which is y minus x divided by the norm, so a unit direction. And along this direction, we have a negative or non-positive inner product with the gradient. And if we do a Taylor series expansion of f around the current point x, we see that if we do a sufficiently small step away from x in the direction of v, then we will find some new point here, f of x plus epsilon v, which will be smaller than f of x for sufficiently small step. So this is a key concept that maybe it's sometimes not so clear to students, and that I like to make very clear. So we have a point, we have a gradient, there is a whole half space where there is all points here are uninteresting from the point of view of minimizing the function f. And all points here, they do not necessarily give us a smaller value, but at least we know that for any direction here, if we do a sufficiently small step in that direction, that we will actually decrease the value of f. So this is the half space which is interesting to search for minimizers. So the point is that if f is convex and differentiable and we aim at minimizing f, then the gradient of the function at the point x defines a set of so-called descent directions, and these are directions that form a negative inner product with the gradient. Okay, so descent direction are those who form a negative in the product with the gradient. And I repeat it, if we do a sufficiently small step away from x in the direction of v, so it means that we move from x to a new point I call x plus, which is x plus alpha v, and alpha is a step size, then we will decrease the value of the function. If alpha is small enough, and we will discuss how to find a suitable so-called step size alpha. And so this is the simple idea, which is the basis of first order iterative methods for unconstrained minimization. We have no constraints here. So we start from some initial point in the domain of the function, and we iteratively update this point according to a recursion of this type. Current point, we take vk as a descent direction, so we use the gradient, for instance, to make sure that vk is a descent direction, and then we choose a suitable step size alpha k, and we update the current point with the new point, and we go on like that. Okay? This way, there is some hope that we actually will eventually minimize this f. We will see why this is true. Okay, so everything is fine if f is differentiable, but what if f is not differentiable at some point? Well, if f is not differentiable, it happens that, but convex, then this relation 1, which is that the fact that the graph of the function is lower bounded by some hyperplane, may still hold for some suitable vectors that I call g of x. More precisely, if we can find a vector g of x such that that relation, that bounding relation holds for g of x, then g of x is called a subgradient of f at point x. And the set of all subgradients, so all vectors such that that bounding relation holds, is called the subdifferential of function fx, and it is denoted by this notation. So this is not partial derivative, it's a notation denoting the subdifferential, which is a set. It's a set, subdifferential is a set containing all the subgradients of a function. So the subgradient is a kind of surrogate of the gradient. When we do not have a gradient, we will happy with a subgradient. Okay? So a subgradient coincides with the gradient whenever a gradient exists, and it generalizes the notion of a gradient at points where the gradient does not exist. So there is a theorem. This can be found in standard books on convex analysis. For instance, in the lecture notes by Yuri Nesterov, and says the following. So if we have a function which is convex and x is kind of interior of the domain, then this set of subdifferentials is a closed, convex, and non-empty and bounded set. If f is differentiable, then the subdifferential contains only one element, and this only one element is the gradient. And moreover, for any direction v, we can always find the so-called directional derivative of f at x along direction v. So this means that we take f is a function of a vector, but if we fix a direction, we can consider the restriction of function f along direction v, and this is a function of a scalar value, scalar variable t. Okay, it's the restriction of f along a direction. Okay, and then we can take a kind of derivative of this restriction of the function along this direction, and this is called the directional derivative. And it turns out that the directional derivative, even for non-differentiable function, always exists. Convex functions exist, and it is related to the subgradient, or better to the subdifferential, via this relation here. Okay. So the point is that, let's say, broadly speaking, I'm not very technically precise, but let's say that any convex function admits at any point a subdifferential, and therefore some subgradient, and therefore a directional derivative, even if it does not admit a standard gradient. Okay, so for a convex function, we have that for all point in the domain, this kind, which is like the first condition that we stated before for convexity. This holds again, provided that instead of the standard gradient, we put here a subgradient of the function. So gx is in general a subgradient of the function at x. So let me give some example of why we need subgradients. They do not arise only on weird functions, even very common functions that we use also in practical applications in engineering. Unfortunately, they may not be differentiable, so we need to resort to this idea of subgradients. So here is perhaps the simplest example, is the absolute value function. Okay, so the absolute value function, scalar. Okay, so function of a single variable. This is the graph of the function, of course, and in this case the derivative is 1. It is differentiable for points that are strictly negative, and the derivative is -1. But when you are at 0, then the function has a kink, so it's not differentiable. So it's not differentiable in 0. Let us find the subdifferential of this function at 0. So we write the function absolute value. We use this trick of expressing the absolute value as a max. So the absolute value of x can be written as the maximum of the product of y times a number which is bounded in absolute value by 1. Okay? And of course the max is greater than or equal to the product for all g which is bounded in absolute value by 1. And therefore, if we compare this to the definition that we gave of what a subgradient is, we see that any vector, in this case, any number which is bounded in amplitude by 1 is indeed a subgradient of the absolute value function. And so actually it turns out that these are all the possible subgradients, and therefore the subdifferential of the absolute value function is this. It's just the sign of x if x is different from 0, and it is a whole interval -1, 1 if you are at 0. Okay? You see, it's in the case where this is just the gradient when the function is differentiable, and this is a set, so the subdifferential when the function is not differentiable. And of course then we can move from absolute value function to another very interesting function in optimization, which is the L1 norm. Very popular in all these lasso type optimization problems. So the L1 norm, well, the L1 norm is nothing but the sum of the absolute values of the elements in the vector. And so if we do again that trick of expressing the absolute value as a max, then we write this sum as the sum of maxima, which is of course less than or equal to the sum of the elements without the maximum taken there. And so this is true, this inequality is true for all vector. Now G is a vector which is bounded in the L infinity norm by 1. Okay, L infinity norm means just that each element of the vector is bounded in amplitude by 1. So for all vector y, it holds that the L1 norm function f at any y is greater than or equal to the value of the function computed at 0, which is, by the way, 0, plus this expression here, where this is a subgradient, and all subgradients are just vectors bounded in infinity norm by 1. So in this way we found the subdifferential of the L1 norm function. So sometimes we can compute subgradients and subdifferentials by direct inspection, and more often we will just use some rules to help us in computing these quantities, the same way we do with standard derivatives. So for instance, everybody knows that when we have derivatives, we can use like chain rules for derivatives, where there are also kind of analogous of the chain rules for derivatives for subdifferentials. Okay, so I don't want to enter into the details, but I will give just a couple of examples of these rules for computing the subdifferential of a composed function. So f of x is the composition. So x is given as an input to function q, and then function q is given as an input of function h, and this gives us f. Okay. And maybe one of the most important or easiest also cases is when we have a linear transformation. Okay, so we have a function h from Rm to R, and then this is composed with a function q, which is an affine transformation of x. So q of x is ax plus b. Okay, and so f of x is h of ax plus b. And in this case, it's easy to see that by using the previous formulas, that the subdifferential of f is just given by what we have to use the Jacobian of this affine transformation, which is A transpose times the subdifferential of h. For instance, take this function. So we considered before the absolute value function of x, but what if we have the absolute value of A transpose x minus b? So this is the absolute value of a linear function of x. But by using that composition rule, we can find that the subdifferential of this function is just, well, what you have here is A, this vector A, times the sign of this if the quantity here is non-zero. So this is the case where this function is actually differentiable. And it is A multiplied, means every element of A is multiplied by a number which is in minus 1, 1, in the case where the argument is 0. So we have this chain rules for computing subgradients and subdifferentials. And there are also other rules like this, the sum or positive linear combination of functions. If we have convex functions and h and q, these are two convex functions, and we construct a linear combination of these two functions, but where alpha and beta are non-negative, so not any linear combination, but a positive or non-negative linear combination. Then essentially it holds that the subdifferential of f is just the sum of the subdifferentials. And an immediate application of this is if we have a f which is a sum of the absolute values of ai transpose x minus bi, for instance, then we apply this sum rule, and we obtain the subdifferential as the summation of the individual subdifferentials. Okay? Another very interesting rule for subdifferential is the so-called pointwise maximum rule. So in this case, suppose that we have a function, our function f is given by the pointwise maximum of a bunch of convex functions fi of x. Okay, so it's the pointwise maximum. Suppose that you have, this is like one function f1, another function f2, another function f3, okay? So this is like f1, f2, f3. I'm considering in this example, of course, a function of one variable. What is f? The pointwise maximum is something like this, okay? So this is function f, the pointwise maximum of three linear functions, for instance, okay? And of course, this functions defined as a pointwise maxima of functions are typically non-differentiable at these breakpoints. Okay. Well, first of all, you might know from convex analysis that if the component functions here are convex, then the maximum of convex functions is also convex. So indeed, f of x is convex. So we may expect that we can find a subdifferential for f. And so the rule in this case is the following one. The subdifferential of f is the convex hull, okay, so the set of all possible convex combinations of the subdifferentials of some of these functions. Not all of them are important, only some of them are important. And which are the important ones? Well, those who belong to the so-called active set, where this a of x is the set of indices here in 1M of the functions that are active in the sense that these are the functions that attain the maximum in the definition of f. Okay? So those indices for which fi of x is actually give us the value of f. For instance, here, if this is the x-axis, and we take a point, like this point here, x, we have these three functions with the active function here. There are three functions, but two of them are not active. The only active function is f2 in this case. So the active set changes with x. At this point here, the active function is f3. And at this point here, we have two active functions. Okay? We have f3 and f1. So at this particular point here, the subdifferential of f will be given by the convex hull of the subdifferentials of f1 and f3. And this actually has, this rule has an extension to infinitely many maxima over infinitely many functions, or where the maximum here is it's actually something like this. We take the sup over some parameter that spans some parameter set, and the function here is actually a function family parameterized by alpha. Then the same kind of rule applies. So the subdifferential is the convex hull of the subdifferentials of those functions in the family, in the parameterized family, that attain the maxima, the maximum, or that are active in some sense. So here is an example of how we can use this pointwise maximum rule for computing subdifferentials. For instance, we may compute subdifferentials of some of these well-known norms like the L1 norm, the L2 norm, and the L infinity norm. All these very innocent-looking functions, they are actually non-differentiable. Okay? Even the L2 norm is not differentiable. Okay? That's why you usually square it. This way it becomes smooth. But if you don't square it, it's not differentiable. So anyway, all these three norms, they have a so-called dual representation. We can express a norm as a maximum of a linear function over a so-called dual norm set. So for instance, the L1 norm can be expressed as the maximum of V transpose X for V that ranges in the L infinity unit ball. And this is actually what I already showed in one of the previous slides. It is just this trick of expressing absolute value as a maximum of something. And something very similar can be done also for the L2 norm and the L infinity norm. So we express this norm as maximum. And so as soon as we express the norm as a maximum over some parameterized family, then we can apply this, the rule I showed you before for computing the subdifferential. So if I take, for instance, the L2 norm case, so the function fv, which is parameterized by v, is just a linear function, v transpose a, x. So of course, for each v, this function has a standard gradient. And what is the gradient of this function? Well, it's v. Okay? The gradient of a linear function, it's v. So what is the subdifferential? It's just the convex sum of all vectors v of the active functions, of the functions that are active. So it's just the convex sum of the active functions. And so this is the set of vectors where this linear form here attains the 2 norm of the vector, where v, the norm of v, is less than or equal to 1. For instance, if we take x equal to 0, then we have that the 2 norm, of course, of 0 is also 0, and so when is this 0 attained by a linear function like this? Well, it is attained for any feasible v. Any v in this inner product gives 0. So any v is active. And therefore, the active set is just a set of v whose 2 norm is bounded by 1. And so this gives us an expression for the subdifferential of the 2 norm. So the subdifferential of the 2 norm of x is, well, if x is different from 0, then the 2 norm is differentiable. So we can find the gradient, and the gradient of the 2 norm is x divided by the norm of x, if x is different from 0. But then this is not differentiable, and the subdifferential is just the L2 ball. Any point, any vector, such that the norm of this vector is less than or equal to 1 is a subgradient. Okay? Another interesting example of computing subdifferentials is for this interesting function. So, consider a symmetric matrix A of x. So A of x is given by this expression where A0, A1, A2, An, these are all known and given symmetric matrices. So the AI, the coefficient matrices are symmetric, and x are variables. Okay, so x is my variable. So I can define a function f of x as the lambda max of ax. So you know that any symmetric matrix, real symmetric matrix, has real eigenvalues, purely real eigenvalues. So the eigenvalues are ordered, and it makes sense to define the maximum of them. So the lambda max. So the lambda max will be some strange function of my variables x. So here we use the so-called Rayleigh variational characterization of the eigenvalues of a symmetric matrix, and it turns out that the maximum eigenvalue of a symmetric matrix is just can be expressed in the form of the maximum of a quadratic form over the unit ball. So the maximum eigenvalue is the maximum of z transpose axz, and the maximum is computed over all z that are on the unit sphere. Okay, this is some more or less known fact in matrix algebra. Okay, so due to this fact, actually we conclude two things. The first thing that we conclude is that, well, let's just rewrite this product here using the definition of AX. If we rewrite it, we have Z transpose A0Z, okay, which does not depend on X. And then we have the sum of this kind of functions. So the first thing we conclude from this representation, if we look at this, for each fixed z, so if you fix z, and you look at this is just a linear function of the variables x. So for fixed z, it's a linear function. A linear function is convex. Then we take the maximum of linear, hence convex functions. So the first conclusion is that this strange function, which is the lambda max, is convex. It is convex because it is the maximum of convex functions. The second conclusion is that by this maximum, pointwise maximum representation, we can compute a subgradient of the function. So what we have to do is to take this representation here and look at the active set. So the active set is the set of those vectors z of norm 1 where actually the lambda max function is obtained. Those vectors, what are those vectors? Well, simply these are the eigenvectors of AX associated to the maximum eigenvalue. Okay? So the subdifferential at this point is just the convex solve of the gradient of the function, where AXZ is equal to the lambda max. So these are the z that satisfy this equation are the eigenvectors of AX associated to the maximum eigenvalue, and where this is the expression of the gradient. In particular, we see from this representation that f is differentiable at a point whenever this set is actually a singleton, and this happens when the eigenspace associated with the lambda max has dimension 1. So when there is only one eigenvector, one normalized eigenvector associated to the maximum eigenvalue. And so this gives, in this case, the gradient of that function. In the case when we have multiple eigenvalues, this formula here gives us the entire subdifferential of the lambda max. Okay, so this is more or less what I needed to tell you about gradients and this idea of subgradient, which is a generalization of gradient. But now let me just in one slide explain why again these concepts are important in an optimization setting. Well, this is I think well known to everybody, the first part at least. So if we have a minimization problem where we want to minimize a convex function f unconstrained, so x can range over the whole space, then if f is differentiable, then the point is optimal even only if the gradient is zero. This is something we maybe learn in high school, probably, right? So the condition that the gradient is zero is necessary and sufficient for optimality of a point. However, if our function is not differentiable, then this is of course cannot hold in general, but the relation that holds equivalently is the following one. So if f is not differentiable but convex, then we have that a point is an unconstrained minimum, so it's an optimal point, even only if 0 belongs to the set of subgradients, to the subdifferential. So the optimality condition is that the subdifferential, the set, contains 0. Okay? So we can use this or this to help us finding an optimal solution in some cases. Okay, so this ends the introductory part of my talk. Okay, so I will talk now about first order and gradient algorithms for minimization. So this citation is just from an ancient book. And you see that the author, it's actually the author who in some way gave the name to the word algorithm. Okay? Was called Musa al-Khwarizmi. That's the origin of the word. So, for algorithm here we just refer to some iterative technique for solving numerically up to some given accuracy, some class of unconstrained minimization problems. And the method I talked about share like a common general structure, a very simple general structure, where at each iteration, k is the iteration count, the candidate point is updated to a new point xk plus 1. And then we check some stopping criterion to see if we are more or less done, and we found our numerically optimal point. And if yes, then the current point is returned as an answer, as a numerical solution to some accuracy of our problem. And otherwise, we do one more step and iterate the process. And the typical update rule, so the algorithm is just an update rule in this case, is of this form. So the new point is equal to the old point plus some step size, scalar step size sk, times a direction vk, which is called the update or the search direction. Okay? And the meaning, the geometrical meaning is again we are at the point xk. Somehow we determine a search direction, for instance, by considering if this direction has a negative inner product with the gradient. So we determine a search direction v, and second thing we do, we decide for a suitable step size, and third thing we do, okay, we do a move to a new point here that we call x plus 1, which hopefully gives us a decrease of the objective value, and we keep on doing this. Okay, so there are some technical hypotheses, because what I want to do now is to give some rigorous, or to some extent rigorous, proof or analysis of convergence, of course, of this kind of idea, because the idea is intuitive and we may intuitively say that it might work, but proving that it works, it's another story. Okay? So we have some assumptions that maybe I don't even need to mention here. They're here. Okay. So the function that we deal with are so-called closed functions, closed convex functions in some cases. It means that the sub-level sets are closed sets. So they contain their boundary. And we assume that the function that we want to minimize is bounded below, so that there is actually a minimum. Like if we minimize a linear function like this function is not bounded below. Okay, we cannot really minimize a linear function because you go to minus infinity and you find no solution. So we assume that it's bounded below, and we define for any initial point. Usually, to start the iterative process, you have to provide some initial point, and I call S0 is just the sub-level set relative to the given initial point. So now, maybe just before lunch, I have a very, very boring part on technical preliminaries. Okay, so please excuse me, but so we need some technical preliminaries and definitions. Maybe most of these are very well known to everybody, but so function is said to be Lipschitz continuous on some domain if there exists a constant such that such relation holds. So it means that Lipschitz means that the function at 2 points cannot vary more than some multiple of the distance between these 2 points. So if the 2 points are close, also in some sense the value of the function at these 2 points must be close in some sense, or at least not too far away. So there must exist some constant that bounds the variation of the function. And then we apply the same idea, but now not to the function itself, but to the gradients of the function. So we say that the function has Lipschitz continuous gradients if there exists a constant such that the gradient of the function is Lipschitz continuous. It means that the gradient of the function should not vary too fast. Okay? So the intuition between this condition 2 is that the gradient should not vary too fast, and it can be proved. A proof can be found in the book by Yuri Nesterov that this condition is actually equivalent when f is twice differentiable, of course, to the fact that the Hessian of the function is bounded by L. Okay? The Hessian of the function is the matrix of second derivatives. Okay? There is no proof here, but you may understand more or less intuitively that since this places some kind of constraints on the rate of variation of the gradient, well, that the rate of the variation is somehow related to the derivative of the gradient, and the derivative of the gradient is the Hessian, and therefore we place a bound on the Hessian. So these are some of the implications that follow from this condition of Lipschitz continuous gradient of a function. So first of all, if the function is twice differentiable, then this Lipschitz gradient condition is equivalent to boundedness of the Hessian. So if you like, the norm of the Hessian is bounded by some constant L for all point in the domain S. Moreover, if F0 is differentiable, then the condition of boundation, of Lipschitz continuous gradient implies this kind of relation on the function. And if you look at this quantity here, which is inside the absolute value here, if you add the hypothesis that F0 is convex, then this quantity here is actually non-negative. Why? Well, it's from the fundamental inequality that I showed in the first slide in the lecture. So when F is convex, this thing here is non-negative. We can actually remove the absolute value, and for convex functions, it holds that this expression here is bounded by the Lipschitz constant divided by 2 times this. Okay, well, so you may start to wonder why do we need all this, and actually it takes quite a while before we understand it. But let me go on with this. One of those inequalities, in particular, this one, also implies something interesting. Implies that the function is upper bounded by a strongly convex quadratic function. Okay? So that inequality means that f0 of x is less than or equal to this thing on the right here. And what is this thing on the right? Well, there is a constant, there is a linear term, and there is a quadratic term. So it means that under that condition on Lipschitz condition on the gradient, our function will be upper bounded everywhere by some, let me call it f up, quadratic, by some quadratic function. And this f up is exactly this quadratic function. So if the function is also convex, we will see that for each point we may construct a lower bound which is linear on the function and an upper bound which is quadratic on the function. So we can sandwich that function at any point. And this is a key aspect in improving convergence of algorithms. So for instance, suppose that x star is the global minimizer that we are seeking. Okay, we are looking for a global minimizer of f0. So x star is the argument of f0. And f0, suppose, is differentiable. Then we know that f0, if f0 is differentiable, then x star has to satisfy to this condition, right? It was the last slide in my previous set of slides. So the gradient of the function has to be 0. So if now we use the Lipschitz gradient condition on f, we conclude this inequality. Okay? Well, this is an explanation of why this inequality holds. And I don't really want to go through this, but it's there. Then I will give you the slides and you can check it. But essentially, so if x is an optimal solution to our problem and the function has Lipschitz gradient, then we can conclude this this inequality here. Okay. So, for instance, if we look on the right at the right right side of this inequality, it says that, well, basically it's not so interesting so far, because it says that, well, if x is close to the optimum value, then also f0, the objective value, will be close to the optimal value of f, which is a good thing to have, but also pretty intuitive one. But then we will show some converse type of implication. So we will actually also reverse this whole thing and see that this quantity here is actually upper bounded also by the norm of the gradient in some sense. So first we have this inequality here. Also, we have that when the function is twice differentiable and the sublevel set is compact, then f0 has Lipschitz continuous gradient. So this point here actually gives us like a sufficient condition that guarantees the fact that the gradient is Lipschitz. Sometimes it's not so easy to see if the function has a Lipschitz continuous gradient, but for instance in this case, this is a sufficient condition for that to hold. So why? Because when the Hessian is continuous, then the norm of the Hessian is also continuous. And if this domain is compact, if S0 is compact, then a continuous function over a compact domain will attain its maximum by Weierstrass theorem. Therefore, we can take L to be just the maximum of the Hessian over this set. And so by definition, the Hessian will be less than or equal to L over that set, which implies, as we've seen in the first result, that over that set the function has Lipschitz continuous gradient with constant L. Alright? Some other preliminaries and definitions. Everybody maybe knows what is a convex function, and there are also other types of convexity. Let's say one is strong convexity. So what is strong convexity? Well, a function is strongly convex when the function minus some quadratic term here, m half norm of x squared, is convex. So a function is strongly convex when there exists a positive number m such that f minus this term is convex. So of course strong convexity is more than convexity. Okay? It's something stricter than convexity. Although there is also a concept of strict convexity which is not exactly equivalent to strong convexity, but I don't want to confuse too much. So from this definition, it follows that if f0 is strongly convex and twice differentiable, so if I take now the second derivative of this function, then it follows that I think that here there is an error. So this should be squared. So this is the Hessian, not the gradient. Okay? So the Hessian is greater than or equal to m times the identity. So sorry, here this is the Hessian, not the gradient. Okay? So for a strongly convex function, the Hessian is lower bounded by m times the identity. But therefore, since for a differentiable function convexity is equivalent to this famous first inequality that we stated in the first slide, and if we apply this inequality to this function here, so f0 minus m, this function here, and we apply this inequality to that function, then we obtain something interesting. We have that if f0 is differentiable and strongly convex, well, if and only if,
then it holds that f0 at any point y is greater than this quantity here. So this means what? This means that at any point there is a convex quadratic function here that bounds from below the graph of f0 at any point. So if we look back at this picture here, we have a function f which is strongly convex. What we can say is that the function, if the function is strongly convex, at any point, not only it can be lower bounded by a linear function, like any convex function, but actually it can be lower bounded by some quadratic function at any point of the domain. So at any point we can find a quadratic function that lowers the actual function. And I call this f low. Okay? And this can be, this function can be obtained explicitly if we know the strong convexity constant m. So now, I want to make it this a little bit shorter than this. So let me come to a conclusion. Well, it turns out that if the function is strongly convex, it is also, we've seen that before, it also has a Lipschitz continuous gradient, okay? I showed that before. So actually, if the function is strongly convex, at any point in the domain, I can find two things. I can find a quadratic upper bound on the function and a quadratic lower bound on the function. So I can sandwich the function in the middle of two convex quadratic functions, one from above and one from below. And here is what I mean. So there is some quadratic function f low, which is less than or equal to f0, and there is another quadratic function f up, which is greater than or equal to f0, and these two functions depend on m, which is the strong convexity constant, and this large m, capital M, which is basically the Lipschitz constant of the gradient of the function. So this is maybe, okay, there are quite a lot of technicalities here, but maybe just the take home.
The second inequality of 0 less or equal than f up, it does not depend on x.
This one?
Yeah.
Yeah, and neither the first does. Well, yeah, it holds for any y.
Okay.
Yeah, thank you. So the take-home concept is that for strongly convex functions, at any point we can bound them from above, from below with quadratic functions. So let us see how what is the consequence of this fact. So suppose that f0 star is the minimum value of the function, which is attained at some optimal point x. So if we write the first inequality, the one for the quadratic lower bound, and since x star optimal means that the gradient has to be 0, then we obtain this first equation here. Using from this inequality, we can actually, I'm skipping some details here, we can actually obtain this second inequality here. And therefore, we obtain this fundamental thing here that in the next, that I put together in this other slide, and this is an important point here. What we obtain is that, so this is the optimality gap. Suppose that we are at a point x. This is the difference between the value f0 at x and the optimal value. and this difference is bounded from above by this quantity here. Okay? So this is maybe the key inequality that we use, because it says the following. If we look at equation 13, it says that if at a point the gradient is small, so you see here we have the norm of the gradient. If the gradient is small, then we are close to being optimal. Okay? That's the key point. So actually in our algorithm, we can check the norm. We can check the norm of the gradient, and if that norm of the gradient goes under a certain threshold, we may say, well, of course we need to know this constant m to do a precise statement. Then we can say that we are epsilon close to the optimum. Okay? But the main point is that as the gradient decreases, also this quantity here, the optimality gap, decreases. Okay, so how much time do I have now? 15 minutes. Okay. So okay, let's keep all these technical preliminaries here. If we need them, we will go back and see how we as much as we need, we go back and check them. So now let's start discussing first order descent methods for unconstrained minimization. So I restate some of the concepts that we stated before. So we have iterates of the form xk plus 1 equal to xk plus some step size sk times a direction vk. So this is the idea. So suppose that we are at a certain point xk in the domain and we have a search direction vk. We can do a Taylor series expansion of f0, and if we do that, we obtain that the function at some new point will be the function value at the current point plus this term here. Okay, this of course up to first order. So the local rate of variation of f0 near xk and the long direction vk is, well, we already saw this in the first slides, is related to the inner product between vk and the gradient. It's related to this rate of variation here, this thing here. So we have already seen that whenever this inner product here is positive, then we have so-called ascent direction and contrary direction vk for which this inner product is negative are called decrease or descent direction. And we have already discussed this. But now let's look again at this inner product. So everything is it's related to this inner product. If we use the Cauchy-Schwarz inequality, the inner product is bounded above and below by the norm of the two terms that I'm multiplying together. And so we notice one thing, important and easy thing to conclude is that the best local decrease, so the minimum of this quantity here, is obtained when Vk is anti-parallel to the gradient. Okay? So the minimum here, so the minimum means this, which is what we want. We want to decrease a lot, at least locally, our function, is obtained when we take Vk to be this. So it's essentially minus the gradient, the anti-gradient, and we normalize it to have norm equal to 1, because this is just the direction. Okay? So this is the reason why this direction here is called the steepest descent direction. It's called steepest descent because it is the direction along which locally this function decreases with the highest rate. You can find also other directions of decrease. Any direction that makes this inner product negative is a decrease direction, but this is the direction of steepest decrease. Just the anti-gradient. So this is a schematic form of a first order descent method. We are given f0, which is a function that we want to minimize. We are given an initial point in the domain and possibly some exit tolerance epsilon. And what we do is at each step we determine a descent direction vk. We determine a step length sk. I'll show you how. We update the current point to the next one according to this simple iteration, and we check some exit condition. If some accuracy is obtained, then we exit and then return the current solution. Otherwise, we iterate and we go on like this, and hopefully we converge somewhere. So let me discuss now. I think I have the time to do this. How we decide about the step size. Okay, how do we select the step size? We already discussed how we select the direction. Okay, the direction has to form negative inner product with the gradient. So, for instance, one choice is take the negative gradient. That's a good selection. It gives you the gradient algorithm that we will discuss. But you may choose also other directions. So the next ingredient is the step size. Why is the step size important? Because I see sometimes students get confused with this idea. Sometimes they think that, okay, if I move in the direction of the negative gradient, I will decrease my function. That's not true in general. You can move in the direction of the negative gradient, even with a convex function, and you may end up increasing your function. All right? This has to be clear, because this decrease is only local. So to make things clear, if you have the nicest possible convex function, like a parabola, like this, okay? And you are at a point here, okay? So actually, you are, this is the variable x, and you are at a point here, and you are using like a gradient descent algorithm to minimize this function. Maybe this is maybe too much elementary, but it's worth saying. So you are at this point, x, k, you compute the gradient of this function. Well, the gradient of this function will be some positive number. So the anti-gradient will be some negative number, okay? So the algorithm will say, move to a new point xk plus 1, so xk plus 1 in this case will be xk, right? So the gradient is, we said it's positive, so the anti-gradient is negative, so it will be minus some step size times a positive number that we don't care. So it means that you move x in this direction. The new point will be on the left of xk. But now, of course, you see from this picture that, well, if you do a small step, for instance, you move from here to here, then okay, we have decreased the function. But if I move too far, then, for instance, I go here, then I have actually increased my function. Alright? So you have to be careful with this. You move in the direction of the anti-gradient, but you have to decide how much you move, how far you move in that direction. And this is the point in this idea of selecting the step size. So what we do? We do the following. We have fixed the initial point xk. We have fixed the direction vk. And we want to find s. So we define this function phi of s. And phi of s is just the restriction of the objective function f0 along the direction given by vk for the negative value of s. So phi is a function of scalar variable. So the most natural approach, the most natural answer would be, well, okay, so let us select as the step size that minimizes phi of s. Okay? So this is the best possible step size that we may choose at that step, because it gives the minimum of the restriction of f0. And this is indeed a valid method, and it's called exact line search. Exact line search. It's called line search because what we do is a search along a line. And the line is, this is the line, this xk plus sv is the line, so we search along that line for the minimum of phi. And that's exact line search. However, this is okay, but we have to solve this problem. And, well, okay, it's a univariate, it may be also non-convex, because here I'm not posing any restriction of f0. The discussion here is valid for generic f0. So maybe finding this S star is costly or not so convenient. So for this reason, this exact line search is not very much used in practice. So we need to find some alternative which consists in searching and looking for usable values of the step size, which are maybe not optimal, but which work in our algorithm. Okay, and so the idea will be to find step size values that guarantee a sufficient rate of decrease in the function phi. Okay, not the minimal, we not find the minimum of phi, but we find any step size that guarantees a certain rate of decrease. In a sense that I will explain. So what we do is the following. So phi of s, again, phi of s phi of s is the restriction of f0 along the line okay, so this is phi of s. What we do is we compute the tangent line at 0 of phi of s, and I call it L of s. L of s is phi at 0 plus S delta k, where delta k is this quantity here, which I choose negative because I'm doing a descent algorithm. Okay? So this L is just the tangent line of phi at 0. So suppose that this is S, this is 0. We have our function phi of s, which may be convex or not. So this is phi of x, phi of s, sorry. And here at 0, we compute the tangent line. Well, it's not a very nice plot, but anyway, this is L of s, the tangent line at 0. Then we do another thing. We compute another line. This is a very, very bad plot, but anyway. We compute another line, which is just, we take L of s and we tilt it a little bit up. Okay? So we build here another line. That I call L bar of s. How do I obtain it? Well, we just take the same expression that we had for L of s, and we multiply delta k by some parameter in 0, 1. In this way, we are just decreasing the slope. Okay? So we have two lines. One is just the tangent line of phi at 0, and the other one is just a tilted version of that line. So now, since phi is bounded below, while L bar is it's a linear, it's a line, so it's not bounded below, for sure that there will be some point where the function phi and this line cross. Maybe more than one point, but at least one point. Let's say this point here. At this point, the line L bar and phi of s, they cross. Okay, and this is, I call this. It's a very unfortunate plot here, but there is another plot in the slide. I call this S bar. Okay, S bar is defined as the smallest point at which phi and L bar cross. So for sure, we have that for all values of S, for which phi of S is smaller than L of S, they provide a sufficient rate of decrease of phi. And this rate of decrease is given by the slope, alpha delta k of L bar. So this condition is known under various names. Maybe the most used one is the so-called Armijur condition. Okay. So the Armijur condition states that the valid step sizes, they must satisfy this condition here. So the step sizes that are valid in this case are all the step sizes that are, on the left of S bar, where there is a sufficient rate of decrease of my function. So maybe, Boris, I will stop here for the morning, and we will continue after lunch from this point here.
Okay.
Thank you.
Thank you.